Hello there. Today we'll be doing number 148. This is a burst balloons. This is a pretty interesting problem. Okay, let's check it out. In this particular problem, we are given balloons with a number of coins available on the balloon, and we're supposed to pop the balloon in the order in which we can maximize the number of coins we can obtain. And the coins in question here is a 167. That is possible because by popping the middle balloon, we can multiply the side balloons and get that value. So in this particular case here, if we pop the 1 first, we get 15 items. Then we pop the 5, and we get 3 times 5 times 8, which is 120. And we multiply that and then we have these 2 balloons left. And we pop the 3 balloon, and when you don't have any balloons to your left or to your right, we will multiply that by 1. And in this case, it's 1 times 3 times 8, which is 24. And we have the last balloon, which we need to pop. And we pop that, and we have 167. Okay, well, in this particular problem, what we can do is try every possible solution, which is a brute force technique, and that would result in, let's see, 2 to the n times n solutions, which is n to the n power. And how I got that is 2 to the n is the height of the the number of items that we need to work with on the height of the tree, because if we take the 3, then we have another 1, 5, and 8 option, and so on and so forth. And then we have each option again. We take the 1, then we have 5 and 8, and 1 and 8, and 1 and 5, and so on and so forth, as you can see here. But the faster way to do it is, if you can see, by selecting the last element, we know for sure what's on the left and right of it. If we select the second last element, we know what's on the what's to the left and right of it. And we select the third last element, and we go in reverse. We could separate these problems into subproblems, which we can solve, which is the key to this particular problem. To do this problem, we first, write up our items that are available here. And we present ourselves with a left and right boundary by which we can work on this particular problem. And with that, we can break it down into subproblems and try every single item from left to right, and break apart the problem. Selecting a 3, we have to only work on 1, 5, and 8. And selecting a 1, we work on 3 and 5 and 8. And we working on 5, we work on 3 and 1 and 8. And we selecting 8, we only work on 3, 1, and 5, breaking down the problem. So let's break down that problem, and let me give you a taste of what we're gonna do. So suppose we select 5, and by selecting 5, we know for sure that the left item and the right item will be 1. So this item will give us a 5. A 1 times 5 times 1. Then we will have to take the left and right of this particular pointer and the left and right of this particular pointer, which is basically left is now I plus 1. And the right is I minus 1. With that, we have 3 and 1. And we still have 1 here. And we have a 5 here, and we still have an 8 and a 1 here. With that, we still can get our 5, 8, and 1. And in the same way, we can get our 3, 1, and 5. Of course, this leaves us with no more items on the left side, and leaves us with only a 3 on the right side, which would evaluate to 313 afterwards. So with that, we have broken down the problem into subproblems, and we have produced a solution together. Okay. The runtime of this, of course, we're going through n items, and in each subproblem, we're going to be running through basically the entirety of all of its I items. Well, n times n minus 1 items, and n minus times n minus 2 items, and so on and so forth, which results in n divided by 2, n times n minus 1 divided by 2. This is the operation it takes for each item that we're going to do, because we're basically we're going to be doing each particular subproblem of each particular item, and starting at a different place. So it would be n to the third power, unless I've gone that wrong. Well, we'll have to write out the algorithm, and we'll check that out. All right, let's go. So nums equals 1 times nums, plus nums plus 1 to introduce those numbers, get the length of nums. We'll be using this variable pretty often. And let's create a DP of a with the left and the right. The reason why we are creating this left and right is because the hash map doesn't work. Yeah, it just does not work because how slow it is for Neetcode. So we'll have to do it this way. The I doesn't matter, so we'll just leave it blank. And there we go. That's our DP. So what we're going to return is DFS of our first item and our length of n, which is n minus 2. Our last item. So let's do that DFS, and let's complete this problem. So left and right. And the first thing we do is our base case is left is greater than right, so we return 0. Else if dp l and r is at this particular location does not equal -1, we're going to return dp of l and r. Otherwise, we're going to set our max coins to be equal to 0, and let's find the max coins for each item. So for I, range of length times r plus 1. So this means that we're going to take the coins equals nums of l minus 1 and nums I and times nums r plus 1. So these are basically going to be the item that we select at this particular point, and the ones and at the end, as shown in the description below. Earlier. Let me just put it out one more time. So 3, 1, 5, 8, and we have, let's say we select the 5. It would be the ones on the side. So just to keep the visual going, make sure that we, have some visuals. So that's important. Okay. So with that, we're gonna add the subproblems, which is going to be DFS of the left side, left, and I minus 1, and plus DFS of the I plus 1 and the right side. And eventually we'll come to a point where left is greater than right. So max coins is going to be equal to the max of max coins and coins. So then after getting the max coins, we're going to set our DP of left and right equal to the max coins. And we can return DP of L and R. It's all the same access. So let's run this, and then let's do the O of n runtime thinking. And the space-time is definitely O of n squared because of the matrix. Left and right pointers. So what we're going to do about the n, let's take a look. So basically, in this particular first loop, we have all the items. In the second loop, I mean, in the second loop, we have like what we're left with is 1, 5. I mean, well, so in this particular situation, we have 3, 1, and 8, and we're doing this for each item. So n minus 1 all the way down. So we're going all the way down to n. So the height of this tree is n. And we're going to, at each level, we're multiplying this by n, n minus 1, and multiplying this by n minus 2, and n minus 3, until it's 1. But the thing is about it is that this is not just n minus 1 operations. We're doing n minus 1 times n minus 1 operations. And this is n minus 2 times n minus 2 operations because we're doing that for loop within the recursion, remember? So n minus 3 times n minus 3, and this is 1 times 1, which is 1. So, let's see. Let's give us a little dot. And of course, this is n times n operations. No, this is n operations. N operations. Yes, n operations. So I concluded that it was n to the third power because of the time it would take for us to go through all of these items. Because of the height of this tree is n, and because each level we're running n minus 1 operations, and we're running it for each operation, which is going to be n minus 1 plus n minus 2 plus n minus 3 for each item. I was thinking that this was going to cost us, I mean, this is basically n squared, and we're multiplying that by n. And when we go down these operations, it's not n, it's not multiplication. Sorry about that. It was n plus. I think it was addition. So with that, we're going deep down. That's just n squared, and we're going n down. So it's going to be n squared to n to a third, I think. So that's my conclusion. It's still on the operations of n cubed. So yeah. This is a pretty interesting problem. If we run it one more time, I think we'll get a faster time. Unless I'm wrong. Because it's the same, I guess, algorithm for this particular time. Yeah, so let's see. So one question would be, oh, timeline exceeded now. Weird. Let's run it one more time. Did I mess up somewhere? I think it's because of this. For some reason, if we do not use an I here, it takes a lot longer. Weirdly enough. Yeah. Anyways, time limit exceeded, right? So in this particular problem, we learned that we needed to break down the problem and find a way to break it down. And the way to break it down was to go from reverse end up until the positive end. And so, yeah, in an interview, I think something that you can get a hold of is divide and conquer, and to find out what must be the case. What are you positive? What must be the case? And so these are two concepts that are most used here that allow us to come to this particular solution. And I think looking out for that is important. So I hope you learned something today. If you enjoyed this video, like and subscribe. Want more videos, check the link in the description below. Thank you very much, and I'll see you in the next one.